Everyone's here. Begin. So today is the last class in the official syllabus. There is one more lecture. What I'm planning to do is I will do that next Monday, but it will not be in your final. Okay, I will do that because that will indirectly make your concept of today's lecture clear. That's why. Okay. So we'll do lecture 14 today, and once we finish, you'll see what I mean. That lecture 15, if I do it, it will just explain lecture 14 better. So that's why I'll do it. But there will not be any direct questions on anything after today. So today is the official last class of the syllabus. Official, exact last class of the syllabus. Everyone with me?
Yes.
Okay. And so next week again, next Monday is optional. Next Monday lab is again optional tutorial, right? For you to check your homework problems. And also I've decided if anybody, I told this to the other section, I don't remember if I told you, you have the option of replacing your worst lab grade if you do an extra lab by yourself. Okay, Ronak will give the lab sheet of the experiment 7. If you do it by yourself, if it's a good mark, I will replace your worst lab mark. So that's just completely optional. So, I mean, if anyone missed a lab, right, or got a penalty on any lab, then you can do this. Okay. Yeah, you can all do it. You can all do it. I mean, if you've got good grade in the labs, then, if you got 8 out of 10 is your worst grade, then you spend the time, how much more can you get, right? So I don't think it would be a productive use of time for people who have good lab marks. For people who don't have good lab marks, then you can try this. That's why. Of course, you can all do it. Yeah. I mean, of course. I guess it's exam time, so right, you have your other course exams as well. But I guess anyone is allowed to do it. And the rule is Ronak will just provide the lab sheet, but I'm sure he'll provide some minimum guidance if you're interested. Right? I mean, I don't want to spend the next lab class on another lab or give you any formal lab assignment now. And because I want to give you next week to study for the exam primarily. And after this exam is done, you have your other exams to study for. Okay.
Sir, is there any way that examটা পিছানো যাবে?
No, because you have a week left, right? Enough time. And pichale, that will not be in your best interest, right? Because it will clash with your other exams.
স্যার আমাদের এক্সাম টাইমটা কখন থেকে?
12:30 next Thursday.
12:30 থেকে কতক্ষণ?
Log in at 12 o'clock. Everyone will see. Maximum 1.5 hours.
আমার 2টা থেকে আমার এক্সাম আছে।
আবার বলো?
2টা থেকে আমার এক্সাম আছে একটা।
আচ্ছা, it will be done by then. Okay. Thanks for telling me. Maximum 1.5 hour. Right? It may actually be 1 hour. Okay. And everyone log in at 12. I'll give you everything before 12:30. Okay. And also the vivas, I will start from next Thursday itself. So next week I'll make up the viva schedule. While I make up the final exam, I will also make up the viva schedule. Okay.
So viva কবে হবে?
So next week থেকে start, next Thursday থেকে over the next 10 days from next Thursday, right? Like midterm time.
মানে স্যার মিড টার্ম শেষ হওয়ার পরে ভাইভা হবে?
Midterm না, final শেষ হওয়ার পরে।
সরি, আই মিন ফাইনাল শেষ হওয়ার পরে।
মানে same process like we did for the midterm. Except এবার vivaতে I might keep a separate question just for viva. So I might ask everyone one new question from any of the slides. Right, last midterm we went over only the midterm question paper.
Yeah.
So final, we will go over the final question paper and there will be one more new question.
Okay.
It's very easily I can pick a random lecture from one slide from the entire syllabus and have each person explain a different slide to me. Okay. Okay. So today we will see some transport layer protocols. And once again, there are three main transport layer protocols. We will see two today. The third one I will show you on Monday. That will not be part of the syllabus, but if you understand that, you understand the full picture well. That's why I still want to do it, even though we will be out of time today. Okay. So we can create a transport layer protocol by combining a set of services described in the previous sections. To better understand the view of the protocol, we start with the simplest one and gradually add more complexity. TCP protocol uses a transport layer protocol that is either a modification or a combination of some of these protocols. So what this slide is saying is we will incrementally build a transport layer protocol using the features or the situations and scenarios we discussed in the last class. I'm sure you're blank about the last class, because as we get into it, it will come back to mind. So that's all this is saying. Once again, that we will build some transport layer protocols using some scenarios there like this. Does this slide make sense? Do you recall this slide?
Yes, sir.
Everyone? Okay. So for these scenarios, we will build up some transport layer protocols to take care of the different issues like packet loss, packet duplicate, how to take care of, how to deal with those. Okay, that's all this is saying. This is the introduction on the book. Okay, so our first protocol is a simple connection-less protocol. Once again, what's the difference between connection-less and connection-oriented?
Connection less or block-gular variable থাকে I mean.
Anyone? Anyone? Think term connection-oriented, connection-less, and connected. Anyone else?
Sir, connected oriented, it makes sure that there is that port address or something, but the other one doesn't make sure that it is.
Right. Exactly. Connection oriented, there are some control messages exchange beforehand. Right? And this one, you just start sending the data without any sort of prior control communication with the receiver. Okay. So, and with neither flow control, nor error control, nor congestion control, we assume that the receiver can immediately handle any packet it receives. So we assume that the receiver has infinite processing power and infinite buffer, right? So this is the first protocol. And like any algorithm development, we will keep on adding complexity, right? Adding variable or adding restrictions. So in other words, the receiver can never be overwhelmed with incoming packets from the sender. Okay, so the first trivial protocol essentially. I guess the correct term is trivial. Right? So just trivial means this. I guess it should use the book uses the term simple protocol, but I like this term better. This is a more technical term. The trivial case means the obvious case, straightforward. This is figure 2370 on the book. So logical channel. So this is once again mark the language, right? This is not a physical channel. So the transport layer feels connected to the transport layer at the other end. Right? There is no direct connection, but the packet from here actually goes through the network layer to the link layer, through the physical layer, through many hops and makes it here. But the transport layer feels directly connected. So according to the transport layer, according to his view of the network, he gets messages from the application layer and he sends it to the transport layer at the receiver end with the correct destination port number. And the transport layer at the receiver end uses the destination port number to route it to the correct application at the receiver. To that direction, and there is a request from the client process or a packet is sent down the protocol stack, packet is sent to the transport layer, and that is given to the using the destination port number. The receiver transport layer sends it up to the correct receiver application. This is the flow. Okay, that's the process. Okay. Just clear to everyone.
Yes, sir.
Okay, to everyone. Once again, we will keep on adding complexity in the sense taking care of eventualities, right? Taking care of possible problems. And the final protocol will be foolproof in this sense, it will take care of all possibilities. So our second protocol is a connection-oriented protocol called the stop and wait protocol, which uses both flow and error control. Both the sender and the receiver use a sliding window of size 1. We discussed this in the previous class, right? Sliding window must be less than half the sequence number space. So here is less than half, it is set to 1. Sender sends one packet at a time and waits for an acknowledgement before sending the new one. So here, so the difference what we're adding is, so in this case, if a packet is lost, in the trivial case, the sender has no way of knowing. So next case, sender will send the packet and wait for an acknowledgement before he sends the new one. To detect corrupted packets, we need to add a checksum to each, right? A parity bit to each data packet. When the packet arrives at the receiver side, it is checked. If the checksum is incorrect, means the packet has been detected to be corrupt and discarded, and no acknowledgement is sent. We use the term connection oriented as well.
Sir, sliding window talk basically key.
Acha, Ashi, good question. Very clear. Acha, hold on to the question. Let me go a little bit. So once you see the application, it'll become clear. Or sliding window from the previous example. Remember, there was a figure with 4 sub-figures. I can go back to it. Let me pull up that slide. Because other people may also have this question. We'll explain it. You see this lecture 13 or no? Oh, I think.
Sir, you just stopped sharing the screen.
Okay, wait. Yeah, there. So is that in this example? Sliding window is, here we use a sliding window of size 7. Right? And so which means you can have, the sender can have at most, first of all, these are the sequence numbers of the outgoing packets, and you cannot have more than this outstanding at the same time. We went through each subfigure in this. The window is 1 through 7. This is the window means sending. Okay, first window means the sending buffer, and sliding window means this window slides forward one at a time as you keep receiving acknowledgements from the back. Get it now? If it's no, please tell me.
Sir, এখন একটু স্যার প্রবলেম স্যার বুঝতে স্যার।
আচ্ছা, does anyone else have issues with this? Let's look at subfigure. Let's go over it again. Let's look at subfigure A. So A case key, my Windows is 0 to 6. 4 packets have been given to the transporter from the application layer. So you will send them using these sequence numbers, right? Starting from 0 to 3. So this is blue means these have been sent. Acknowledgements for these have not yet been received. So that 0 is the sequence number of the first outstanding packet, first one that was sent, and 4 will be the sequence number of the next packet to be sent if necessary. So in B, we see that application layer has now given you another packet to send, and previous acknowledgements have not yet arrived. So you will send the next packet with sequence number 4, right? And your sequence number of next packet, this variable will increment to 5. Suppose here the application layer has given you 2 more packets. You will send them with sequence numbers 5 and 6. Now your sending window is full. So unless you receive any acknowledgements, you are not allowed to send any more packets. You cannot have more than 7 outstanding at the same time. You don't know if these have reached or not. Now in D, first acknowledgement for packet 0 has arrived. So now your sliding window will slide forward one step. So you have received acknowledgement for packet 0, which means this has reached safely. And the acknowledgement has also arrived safely, which means you also know that it has reached safely. It's possible that the packet reached, but the acknowledgement got lost. Right? But in this case, okay, acknowledgement has also arrived at the sender. So you know the 0 has reached safely. So this means 1 is your first outstanding packet, or the last one that is still outstanding. And because this has acknowledgement of this has been received, your window slides forward one step. You're now allowed to send one more packet out with sequence number 7. So then
that means it will go on.
Exactly, this will keep sliding.
Okay, so then it would be for the next packet, it would be for 2.
So
right?
suppose you get 3 more acknowledgements, which means suppose packets 1, 2, and 4 have been acknowledged. For packet 3, the acknowledgement got lost, everyone. Exceptional scenario. So then you will only slide forward 2 steps. You cannot slide forward to 4 because 3 is still remaining.
Yes,
If you
sir.
slide forward 2 steps, right, then you will have 8 and 9 open, which means you are allowed to send 2 more packets from the sender side. Yeah. Okay, and this is the same thing in a linear format. So next, that's what I'm saying. So today and the next class, we will see different detailed exceptional scenarios. And the final protocol will handle all exceptions. Okay. Can you see lecture 14?
Yes, sir.
Everyone? Okay, good. Okay. So in this case, the sliding window is of size 1, which means you can have only one outstanding packet at the same time. Right? Which means the sender sends one packet at a time and waits for an acknowledgement before sending the next one. Do you realize? Right? So because sliding window is size 1, this means before the packet 1 is realized, you cannot send the next packet.
Right, sir. So
Right.
if this package is lost, then it will again send it for acknowledgement, right?
So there will be a timer at the sender. If an acknowledgement is not received before the timer expires, then you resend it and you assume it's lost. Then to detect corrupted, we need to checksum to each data packet. Right? Packet was received, it is checked. If the checksum is incorrect, packet is corrupted and silently discarded. So there, send window of size 1. There is a timer. So packet is sent. Acknowledgement is received. Right? These are the logical channels. So in the packet, there is a checksum field and a sequence number. And in the acknowledgement also, there is a checksum and an acknowledgement number. So the acknowledgement has no data. That's why the acknowledgement is a smaller packet. It's just saying this packet with this sequence number has been received correctly. Right? There is no data being sent. Next. So next, here you can realize that in this scenario, since my sender window is size 1, my sequence number space can be limited to 2 values, 0 and 1. So as though we have used x as a sequence number, we only need to use x plus 1 after that. There is no need for x plus 2. Can be limited to 0 and 1. This will be clear as I give some background. In this case, a sequence number only needs to be 2 values. A 1-bit sequence number will be sufficient. Acknowledgement number always allows the sequence number of the next packet. Okay, this is a protocol issue. Somehow, protocol has been that if you send packet 0, acknowledgement value will be 1, not 0 in the sequence number. Everyone. So somehow the terminology or the interpretation has been acknowledgement the receiver will say which is the next packet I want to receive. You see the reasoning? Somehow this has become the convention. Any convention would have worked. The convention has been the receiver will provide a value of the next packet it is expecting or it is able to receive, which implies that it has received anything up to that. So if you're sending packet a sequence number X, the acknowledgement number will be X plus 1, meaning everything up to X has been received. Are you with me? This is just an interpretation issue, right? Now, as long as both are aware of the convention, this is fine. Okay. So acknowledgement numbers by convention always announces the sequence number of the next packet expected by the receiver. Actually, add this as well. So, for example, if packet 0 has arrived safely, receiver sends an accurate ACK number equal to 1, meaning packet 1 is expected next. Are you with me? It's just an alternative way of saying, of giving the same information. But as long as both sides are aware of the protocol, the system will work. So this shows an example of a subordinate protocol. Packet 0 is sent and acknowledged. Packet 1 is will go through the figure. Packet 1 is lost and resent after the timeout. Resent packet 1 is acknowledged and the timer stops. Packet 0 is then sent and acknowledged, but acknowledgement is lost. We will see all possible cases. Sender has no idea if the packet of the acknowledgement itself is, if the packet itself or the acknowledgement is lost. So after the timeout, resets packet 0, which is acknowledged. So packet 0 is packet 0 is sent. Okay, so the send window of size, your window is now at 0. 0 is sent, packet 0 has been received, everyone, which means the receiver is now expecting or able to receive next packet. Receiver will receive will be packet 1. So he will send an acknowledgement with value 1. Now, sender knows the protocol, right? Knows that the receiver acknowledged value is 1 means receiver is now willing to or expecting or able to receive packet 1. So he sent, which means packet 0 has been received correctly. Is everyone with me? Please mark every word. So the sender window will then increment for value 1. Now, if the application layer gives the transport layer the next packet, he will then send it with sequence number 1. Okay. In this case, obviously, yes.
Sir, the sender has the next packet 1.
Receiver does not know. Receiver is saying when the sender sends, he will receive, and he will wait.
Sir, I think
right?
so it should. So is it acknowledgement 0 or 1?
This one.
For the packet 0, the
for packet 0. So this is our terminology, our protocol.
Yes,
and the protocol is, instead of saying I have received 0, it's the same thing. It's just another way of saying it. He will say I am ready to receive. Instead of saying I have received X, he will say I am ready to receive X plus 1.
Yes.
Right?
Yes, sir.
Right? Which means I have received everything up to X.
Yes, sir.
Right? Okay, I have received X minus 1, everything up to X. Okay. So X value 1. So this acknowledgement, the assumption is it arrives before the timeout expires. So the sender knows this has been received correctly, which is why receiver is expecting 1. Now, whenever the application that gives it the next packet, he will send this. In this assumption, this packet has been lost. So, like you're saying, the receiver does not even know that it has been sent. So the receiver does not have a timer. Now, this is lost. Obviously, the acknowledgement does not arrive. The receiver doesn't know that doesn't even know that it has been sent in the first place. So the timer expires. The timer expires. Sender thinks either the packet is lost or the acknowledgement is lost. He has no way of knowing. He will resend packet. So assumption this has been received correctly. Receiver will again increment. So this is 0 now, right? So next one is expecting is 0. So he will send acknowledgement 0, which means 1 has been received. Now, the sender receives this acknowledgement. He interprets that to mean that means the previous packet has been received. So this will again increment by 1. Then next time the application layer gives it a packet, he will send it with packet number 0. In this case, assumption is packet has been received. So he will then again increment this. So the acknowledgement number will be 1. Now the acknowledgement is lost. So here again, within the timeout, if the acknowledgement does not come, sender has no way of knowing whether the packet got lost or the acknowledgement got lost. He will resend the packet itself. Now, at the receiver, packet number, sequence number is 0, but he is expecting 1, right? So he knows that this must be a duplicate. He will discard. He will discard. He will send acknowledgement 1 again. Because from here, once he receives a duplicate, receiver can interpret that means the acknowledgement got lost, which is why the sender had no way of knowing, which is why the sender had resent. So he will resend the acknowledgement, previous acknowledgement. So this actually takes care of all possibilities. You cannot have a duplicate packet. Take a moment.
Sir, if in the sending side, so the series is the packet series is 0000, so then how will the receiver receive it?
Say it again, if the
Sir, in the packet series, sir, if it is 0000, so then
no. Your sequence numbers are alternating between 0 to 1, right?
Yes, sir. Yes, sir.
So that's why, remember, your sequence number, as said in the last class, your window size must be less than half the sequence number space, or sequence number space must be double the window size.
Yes, sir.
If the sequence numbers, if your window size is of size 1, the sequence number space must be size 2, at
Yes,
least.
sir.
And size 2, here we see size 2 is sufficient. Size 2 means 1 bit, value 0 and 1, and that is sufficient.
Yes, sir.
Now, so we see that the name of this protocol is called the stop and wait protocol. So you send one and you stop and you wait for acknowledgement. So this stop and wait protocol, while this is correct, this is very inefficient. Inefficient if our channel has a large throughput. Large throughput means you're able to send many bits at a time, many packets at a time, right? And a long round trip delay, which means, essentially what are you doing? You're sending one packet and you're waiting for the acknowledgement before sending another one. So while this protocol is correct, imagine if this is a system where packets getting lost is very rare. 1 in 100 packets get lost. So then, if a modification you're likely to make is you're likely to say, I will send a few, let's increase the window size, let's send a few at a time. On the rare occasion, if a packet gets lost, I will resend that, right? But you see here, in the entire time flows vertically. So in the entire times, the time period, you're sending for a very small fraction of these times. So while the system is correct, it is very inefficient, especially if the channel has a large throughput, which means you're able to send out many packets at a time and long round trip delay. You have to wait a long period for the acknowledgement. The product of these is called the bandwidth delay product. We can think of channel as a pipe, and the bandwidth delay product is the volume of the pipe, essentially in bits, as an analogy. So there's some trivial straightforward math in this. So assume that in a submarine system, the bandwidth of the line is 1 Mbps and it takes 20 milliseconds to make a round trip. There's a bandwidth delay product, which basically means you multiply them. The system data has data packets are 1,000 bits in length. What is the utilization percentage? So bandwidth delay product is essentially you multiply these two, comes up to 20,000 it's bits per second times seconds. So answer will be in bits, right? Bits per second times seconds. So bandwidth delay product will be in bits. System can send, this means the system can send 20,000 bits during the time it takes for the data to go from one sender to the receiver and the acknowledgement to come back. However, the system sends only 1,000 bits. That's what it's saying, right? In this one cone, essentially one, it's sort of like a cone, packet to go and the acknowledgement to come back. In this time period, in this example, you could have sent 20,000 packets, but you have sent only 1,000 packets, 1,000 bits, sorry, right? One packet, 1,000 bits, whereas you could have sent in the 20 milliseconds using a 1 Mbps transmission rate, you could have sent 20,000 bits, everyone. Very obvious. Everyone with me? Right? That's what it's saying. The concept is, if we did this example, it's a 1 Mbps line, 1 megabits per second, and it takes 20 seconds to make a round trip. So if this speed is 20 seconds, and you can send 1 megabits per second. So in this 20 seconds, you could have sent 20,000 bits. You could have sent 20,000 bits. Can you see, guys? Or the presentation to chole geche?
দেখতে পাচ্ছি
Oh, okay. Right. So you could have sent 20,000 bits, right? But you send only, you have sent only 1,000 bits. So you've utilized only 5%. So this protocol, while correct, the definition of correct protocol means packet losses can be detected and recovered from, duplicates can be detected and recovered from. So this protocol will work, but it is inefficient. Next. Suppose you have decided, you have modified to allow 15,000 packets before stopping about the 15 packets before stopping and worrying about the acknowledgement. Question, anyone? Question, anyone? Okay. So this case, bandwidth delay product is 20,000. Previous case, system can send up to 15 packets or 15,000 bits, which means utilization is increased. But of course, if there are damaged packets, utilization percentage is less because packets have to be resent. But this will work assuming no packet errors, or so essentially you will use this in a channel where you know that packet getting flipped is a low probability. Okay. So this example we saw, this is the term called pipelining, which means task. I mean, the technical definition, you should have seen this in your computer architecture class. Task is often begun before the previous task has ended, essentially doing things in parallel. So this is, the technical term is pipelining. In the stop and wait protocol, there is no pipelining because the sender must wait for a packet to reach the destination and for the acknowledgement to reach the sender from the receiver before the next packet can be sent. And pipelining improves the efficiency if the number of bits in transition is large with respect to the bandwidth delay product. So essentially, right, it means what we have seen in this example and many at a time. Right, hello. Let's take a 2-minute break. What will like 30%. Okay, camera 30 पे कहते हैं variant slide. Okay, guys, 2-minute break. All right, guys, let's continue. Not necessary anymore. So we will start. We've seen the stop and wait protocol, and see that while it is correct, it is inefficient. Next is okay. So to improve the efficiency of transmission, multiple packets may be in transition while the sender is waiting for an acknowledgement, right? In other words, we need to let more than one packet be outstanding to keep the channel busy while the sender is waiting for acknowledgement. Yes,
I think this you have stopped sharing the screen.
it's not being presented. Okay.
No, sir.
Okay. 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 So, to improve the efficiency, multiple packets must be in transition while the sender is waiting for an acknowledgement. Essentially, there's no need to, wait for one packet at a time before you send the next one. If you know that packets or acknowledgements getting lost is a rare scenario, right? Then there's no need to wait for confirmation for each and every packet before you send the next one, right? So we let more than one packet be outstanding to keep the channel busy while the sender is waiting for acknowledgement. So the first of such protocol we will see is called the go back N protocol. The name will be clear once we see the. So in this case, we expand first. We expand the sliding window, the window size to more than one, right? We increase the sequence number space and also the sliding window to more than one. So in this example, the sliding window is of size 7. Okay. So then the variables are, this is the first outstanding, which means has been sent but not yet acknowledged, like previous case. This is the SN or next one to be sent out, or that may be sent out if the application layer gives it another packet, another message. Receive window is still of size only 1. We will see why. Okay. So send window, receive window still of size 1. Send window is of size N. And there are two variables, which is SF or first outstanding and SN, which is next to be sent out. Next, that may be sent out. And there is a timer. So again, packets flow in one direction, acknowledgements flow in other direction. Acknowledgement, once again, we follow the same protocol. That acknowledgement number will provide the number of the next packet to be received, or next packet that may be received, which means everything up to that has been received. Okay. So sequence numbers are modulo 2 to the power m, where m is the size of the sequence number field in bits. Acknowledgement number in this protocol is cumulative, which is, it means if a sequence number of the next packet expected, which means everything up to that point has been received. So for example, if the acknowledgement number is 7, this means all packets with sequence numbers up to and including 6 have arrived safely, and the receiver is expecting the packet with sequence number 7. Everyone, please take a moment. Everyone okay? Anyone not okay? Once again, it's up to today is part of the syllabus, and as questions on these parts is to give you different diagrams of this sort. Give you different diagrams of this sort, and from the diagram provide this list, or to give you this list and have you draw this diagram. This is the typical question from these topics. Right? Either draw this timing diagram or called a flow diagram once the scenario is listed, or once the flow diagram is given reverse direction, list the various scenarios. Because this will test your detailed understanding of the algorithm, right, of the protocol. So that's what I'm saying. Please try to understand in detail. And we'll see when yes.
জিবিএন প্রোটোকলটায় স্যার আপনার বেসিক্যালি আমি স্যার এখানে শুধুমাত্র যখন আমার কোনো প্যাকেট মানে পৌঁছাতে পারবে না ওই প্যাকেটটা কি শুধুমাত্র রিকোয়েস্ট করব, বাট আমি কিন্তু মানে আমি কি স্যার ততক্ষণ পর্যন্ত নিতে থাকবো?
তোমার ওই কোয়েশ্চেনের দুইটা আনসার হবে, we will get to it. Right? There are two ways of dealing with that. And GBN deals with one way. We will do something called GBN plus, which deals with it the other way.
Okay.
And that is why Onno protocol jeta bollam is the next class. I don't have time to do it today. We will do it in the next class to complete your understanding of GBN. Even though I will not directly ask questions on that. That's why I said I should still do the next lecture, because that will improve your understanding of this particular topic. So, and let's see scenario. So once again, AJ. First outstanding, right, is this. So this is blue part, outstanding, which means sent but not acknowledged. White part can be sent when accepted from above process, right? And together is this the window size. Before this is which packets which have been sent and which have been acknowledged as well, right? Acknowledgement have also been received, which is why the window has moved forward. And to the right, this is cannot be accepted from the application layer process.
তার মানে হচ্ছে যে আমার যখন মানে লাইক অ্যাপ্লিকেশন লেয়ার থেকে যদি আমাকে রিকোয়েস্ট করে আরো 3টা প্যাকেট দিতে, ওই ক্ষেত্রে স্যার তখন আমার এই 3টা ফুল হয়ে গেল, এরপর হচ্ছে যে আমার বাকি থাকলো 7 আর 0.
Exactly. মানে এখানে you are allowed to accept 3 more packets from the application and send those. You cannot accept anything more unless any
application layer is requesting for that.
Unless these have been acknowledged. When these are acknowledged, this will slide forward. Then can you accept? Okay. Previous case, remember, stop and wait. Your window size was only 1. You could only send 1 at a time. Now at least you can send 7 at a time.
Got it, sir.
So send window is an abstract concept defining an imaginary box of size through the m-1 with 3 variables, SF, SN, and S size. S size is the size. SF is the first outstanding. SN is the next one to send, which means, so you know all every box basically, right, using these 3 values. On SF to SN, this part is blue, which means outstanding, which means sent but not yet acknowledged. Between SN and size and S size, these are the values which can be sent. And from SF plus S size is your window size. So using these three values, you can define the full box. You have the full information. Okay. So next, sliding the send window. So once any is received, this is slide forward, right? So in this scenario, window after sliding and act with acknowledgement number 6 has arrived. So now acknowledgement is cumulative, which means their window before sliding, packet with acknowledgement number 6 has arrived. Act number 6 means receiver is expecting packet 6, which means it has received everything up to 6, or right, up to 6 means up to 5 basically, including 5. 6 is the next one it's expecting. So you have actually slid forward 2 steps, everyone. Slid forward 2 steps on this side. So one acknowledgement has acknowledged multiple packets. Sliding direction. Now receive window. So receive window is still size of 1 is sufficient. So receive window means this is next expected packet, which means 0 through 4 already received and acknowledged. This is the next one you're expecting. You cannot receive after this. You can receive 5. Once you receive 5, you will slide forward by 1. And now in this scenario, suppose it has sent acknowledgement 4, right? Acknowledgement, once it sends acknowledgement 4, it will slide forward 1 step and wait for 5. Everyone. Suppose this acknowledgement got lost, what will the sender do? Right? If the acknowledgement gets lost, sender will not be able to slide the sender window forward. So after the packets have timed out, sender will resend these blue packets again. At the receiver, you will receive duplicates of these. So once it receives duplicates, it will know that means this acknowledgement got lost. So it will resend the acknowledgements. It will not accept.
That means it will send the same thing again, right?
It will send the previous 4 again, exactly. Or actually, it will send acknowledgement number 5, which will indicate that it has received everything up to 4. And once the acknowledgement 5 is received, sender will slide the window forward. So every scenario will work in this protocol. Every problem will be fixed, right? Will be addressed, can be detected. Sorry, not that can be detected.
স্যার রিসিভ উইন্ডোর স্যার সাইজটা স্যার 1 হচ্ছে হয় কেন?
1 এর বেশি দরকার নাই. Receive window only needs to inform, first of all, if it's small, you're saving memory. And
Oh, sir, I got it.
দরকার
It's
নেই,
used
right?
for স্যার এটা স্যার তাহলে স্যার শুধুমাত্র অ্যাকনলেজমেন্ট হইছে নাকি এটা জানার জন্য ইউজ করা হচ্ছে,
Now,
রাইট?
receive window is saying you can receive once. Suppose sender has sent out multiple packets. Receive window, once it receives 5, you will increment by 6, then you will receive 6, then you will receive 7.
স্যার বুঝছি স্যার
Right, increment 1 at a time. Problemটা হবে এই সিনারিওতে, suppose packets have been reordered in transit. 7 has arrived before 5. If it receives 7, it will drop 7. It will discard 7. Cannot be received. If you receive 5, it will send acknowledgement for 5. If they arrive sequentially, it will increment 1 at a time. If these packets arrive out of sequence, receive window will have dropped the forward later packets. So in this case, the sender will be forced to resend these packets again.
স্যার এখন যখন আবার নতুন প্যাকেট করে পাঠাবে স্যার তখন রিসিভিং এন্ডে স্যার ওরা ওই স্যার যেইগুলো পেয়েছে স্যার যতটুকু পর্যন্ত বাকিগুলো ড্রপ করে দিয়ে আবার শুরু থেকে শুরু করবে, রাইট?
Exactly. So this will work, right? What you're saying is there can be still a sense of inefficiency in the system. But
Yes,
this
sir.
is more efficient than stop and wait, and this is while still being correct. আবার বলছি this is a new term in networks. Correct protocol means corner cases can be resolved. right? Exceptional scenarios can be resolved. Next protocol we will see will have receive window incremented as well to store out of order arrivals. So in this case, receiver will discard all out of order arrivals. So this is still more efficient than stop and wait, but there is still room for improving efficiency. So in go back end, size of the sender window must be less than 2 to the power m. Size of the receive window is 1. So in this case, if your sequence number bit is 3-bit, you can have up to 6. Previous case when I said must be less than, half of this is in the next algorithm we'll see, next protocol we'll see. Okay. So stop and wait is a special case of go back end with send window equal to 1, and receive window once again is 1 in both cases. Another couple of more minutes. So although there can be a timer for each packet, in our protocol, we use only, we don't have to use more. So in this case, one good thing is, with the time of the first outstanding packet expires, we must resend all outstanding packets. Now this should make sense to you. If packet 4, let's say, has not been received, which means even if the other packets had been received, the receiver has discarded them. So you don't need a timeout for every packet. You need a timeout for only the first outstanding packet. Right? And if the first outstanding has expired, you must send this, which means you must send everything after this again. So the transport layer actually keeps copies of these once the application layer has sent it down. So I guess this statement should now make sense, right?
Yes.
Right. I'll tell you which one. Oh, sorry, this paragraph. In this, what we're actually doing is that we start with the simplest one and gradually add more complexity. So we are actually building up a TCP protocol, starting with the trivial and adding more complexity. First was assuming there is nothing that can go wrong. Right? First, we assume nothing can go wrong, no capabilities. Then we assume packets can get lost, so we added the acknowledgement. We added the acknowledgement scenario and 1-bit uh, sending window receive window of size 1. Then we see while this is correct, this is inefficient. So we add some efficiency by allowing the send window to be bigger than 1. The receive window is still 1. We added efficiency. So when the timer expires, the sender resends all outstanding packets. For example, suppose the sender has already sent packets. Right? So suppose sender has already sent packet 6, right? Sn equal to 7, but the only timer expires. If SF is 3, this means packets 3, 4, 5, and 6 have not been acknowledged. So sender goes back and resends all of this. This is why this protocol is called go back n. On a timeout, the machine goes back n location, the resends all packets henceforth. Okay. It's one more animation, just one more slide, and we'll finish. Stop for the day. So I can say no more. And so different scenarios with the window size of slice. So here 3 bits for M, sorry, M is 2 bits. So 2 to the power M, sequence number space is 4, everyone, 0 through 3. M equal to 2, so sequence number space is 2 to the power M, a window size must be less than that, so window size has been set to 3. Okay, so scenario is saying packet 0 has been sent, then packet 1, so the application layer gives it packet 0, packet 1, right, and packet 2. So 0 has been sent, let's say packet has been received, which means receive window has incremented to 1, he's expecting 1 next, he sent acknowledgement number 1, meaning up to 0 has been received, ACK got lost. Since the ACK did not arrive, sender did not increase the sending window, did not move the slide the sending window. He sent packet 1, 1 has been received. Receiver is expecting 1, so receiver accepts packet 1. That's fine. His sliding window, receive window slide forward to 2. Sends ACK 2, meaning everything up to 1 has been received. This ACK supposedly also get lost. Sender, so since the acknowledgement has not been received, the sender does not increment his window. He receives packet 2 from the application layer, he sends packet 2. Suppose this has also been lost, he has sent out, right? The packet receives correctly, ACK sent, ACK 3, meaning up to here everything received, this ACK also got lost. Okay? Now in this case, sender window has not increased. Sender has timed out by then. He will resend packet 0. Now the receiver is expecting 3. If he gets packet 0, receiver will know this is a duplicate. He will discard the packet. He will send. What will he do now?
So again send another acknowledgement packet.
And with ACK number?
With Act 3, sir.
ACK number 3. Very good. So in this case, we needed to make sure that the sender window is maximum 2, not 3. If the sender window had been 3, right? Sender would have sent out packet 3, could have sent out packet 3.
Yes, sir, but in that
Which
case,
he would have received, but then he would have said receive packet 0. He just would have moved to 0, which would actually was actually packet 4 from the receiver's point of view, but packet 0 from the sender's point of view. So we cannot allow that to happen. Does everyone get it? We cannot let the receive window move to 0 before this 0 has properly been acknowledged.
yes, sir.
So that's why the sending window must be less than 2 to the power m. For this, for the scenario where receive the 2 zeros, I mean 2 numbers do not mean different things at the sender and receiver. That's why here if this moves to 0, this would actually be number 4, whereas for the sender, this is actually number 0.
So here M is the number of packets, right?
Say it again.
M, sir, number
No,
of
M is the bits in the sequence number field. Guys, I need a minute. Hello? Okay. So another scenario. Once again, right? So questions on these protocols of this are of this sort. I will give you, like I said, a list of steps, tell you to draw the diagram, or give you the diagram, tell you to list the steps of what's going on, because that tests the understanding. It's another scenario. So there, if the size is m, what happens? So packet 3. So this is we're talking about an extreme scenario, right? Where all packets received correctly, but all acknowledgements get lost. So 3 gets lost, it sends packet 3, right? Received goes to 0. So here acknowledgement 0 means he's expecting packet 4. Now the sender times he sends packet 0. So erroneously accepted and delivered as new data. So he sent packet 0, which the receiver interprets to be packet 4, which the receiver actually is supposed to delete, right? Because it's actually packet 0. Packet 0 resent, but which is erroneously accepted and delivered as new data. So this will happen, one second, if the sender window is limited to 2 and not 3, right? Or size 3 and not size 4. Yes.
স্যার এটা তো স্যার তাও অ্যাপ্লিকেবল হবে না স্যার, রাইট?
আবার বলো অ্যাপ্লিকেবল হবে না মানে?
স্যার মানে বুঝেছি স্যার, এটা যদি মানে আমরা যদি সেন উইন্ডো সাইজ যদি 2^m এর সমান রাখি স্যার, ওই ক্ষেত্রে স্যার তাহলে আমার
If your send window is of size less than 2 to the power m, the protocol will behave correctly under all scenarios. If it is not less than 2 to the power m, so a scenario where it is equal to 2 to the power m, then there are scenarios where your protocol will not work correctly, which is saying, right? So I'm proving by counter example, which is saying the send window must be less than 2 to the power m. So I'm proving this by counter example.
Sir, one question, sir. In the first scenario, so why the receiver will send act 3 again, sir?
In the first scenario,
Sir, why will receiver send act 3 again?
okay, receiver, what is our receiver protocol? Receiver protocol is act number will be the next one he is expecting. So he sent act 3 means he's expecting act 3 next. Here he receives packet 0, right?
Yes, sir.
But he's expecting act 3. He's expecting packet 3. And his
Yes,
way of saying that is act 3, which is his way of saying I have received not just 0, I have received everything up to 2 correctly. If he sends act 0, that means he has received up to -1 or the previous 3 correctly, right? Saying act 3 means he received everything up to 2 correctly.
Yes, sir, but act 3 got lost.
Right. He doesn't know which one got lost. But he interprets exactly that the previous act got lost. Previous act 3 got lost. He will resend act 3. And if in this scenario, suppose he resends act 3, if this is received correctly this time, the send window will advance 3 steps at a time. It
Yes,
will
sir.
be 3, then 0, then 1. The send window size will be 3012, or sorry, 301, 3 values, 3, 0, and 1.
Yes, sir.
Okay, good. Okay, next, I will not go through these myself. There are more examples. Please go through these yourselves as practice. Right, more examples. List, and then the diagram. Different possibilities. Another list, another diagram. Right. So I will assign more homework, and next class we will see the next algorithm once again, which will just explain this one better, essentially. We will see one more algorithm. That's what I'm saying. So the next protocol will not be part of the final, but doing the next protocol will improve your understanding of these flow diagrams, improve your understanding of the ones that are in the. and I will assign the homework today. So take a moment, everyone. That's what I'm saying. Like, go through these examples yourself. Right? Next one, go through it yourself. Obviously, there, I know you can assume, pretty well assume there will be a question on this, right? On these timing diagrams, flow diagrams. All right, guys. So next we meet next Monday, and make sure you will assign homework 6. Right?
Okay, sir.
This is the official part of the syllabus. And next week we have class on Monday. We have class on. I mean, we are meeting on Monday, meeting on Wednesday. So obviously, I'm available to answer questions and available on email, right? Okay. Usually, I try to take my exam ahead of time for 2 purposes. One, it gives me time to check scripts, right? Second, you are also not having all your exams back to back. And because I do that, I try to finish my courses also a week before to give you time to study as well. I'll make some changes to the slides, so I'll upload the new one. Okay. All right, guys. See you on Monday. Bye.
Hi, sir.